Welcome to our next lecture in the series on condensed matter theory. In this lecture, I want to have a look at the vacuum Green's functions for systems without explicit electron-electron interactions. The Green's functions that we've used so far for the retarded as well as the advanced Green's functions are valid for any interactions that one encounters. At the same time, when you look at the definition of our Green's functions, then they still include the wave function of the ground state. And representing the ground state wave function for a many-body interacting system is very difficult and can scale exponentially with your system size. So we would like to find ways to calculate our Green's functions without the need to calculate the ground state. So can we calculate our Green's function without knowing what our ground state wave function is? And if our Hamiltonian is of the form where we have only one particle interactions, so we have a Hamiltonian that in second quantization is annihilating a particle from one quantum state and creating it in another, then it will show that we can represent easily the Green's function without knowledge of the ground state wave function. So, can we calculate G plus tau prime omega without calculating the ground state? And for a mean field approximated Hamiltonian, or a Hamiltonian where we only have potentials, that answer is yes, that is something that you can do. And not only for periodic Hamiltonians where you already know how to block diagonalize your Hamiltonian, but for any Hamiltonian, even when you have no symmetry and many particles. Now, the general Hamiltonian includes not only interactions that are of the form of a potential, where we have the interaction between two particles or creation and an annihilation operator, but we have also the interactions between two particles where you have two particles scatter, two particles annihilate, two particles create. For example, the Coulomb interaction, U, that now depends on 4 quantum numbers, where we create 2 and annihilate 2, tau prime, tau double, tau triple. Now, the good news is that even for Hamiltonians of this form, you can calculate the Green's function without the need to calculate the ground state wave function. But there is a big but. Might be difficult. It might be a lot of work. But there are systematic ways that you can start and improve and make things more and more accurate as you go on. So during this semester we'll have a look only at the mean field approximated, and then next semester we'll also discuss the interacting case. But let me give you a flavor why it becomes much more difficult when we have two particle interactions. Let's say we start with our state in the ground state. So we have our ground state, and I can represent my ground state by densities of states. I have, as a function of energy, some set of states, and the states below the Fermi energy are filled, and above the Fermi energy they are empty. Then at t equals 0, I create a particle in my system. And up t equals 0, we are in an eigenstate, so there is no change. and this is E dagger tau prime psi 0. So here we have our quantum state tau prime, and I have now filled this with one electron. This electron, of course, must not be in an eigenstate, so it can propagate and it can move through all unoccupied states. And this is exactly given by the one particle Hamiltonian. You can annihilate it from tau prime and create it somewhere else, and then it can just move freely from state to state in the unoccupied part, as long as you're not in an eigenstate, because then it would just only change its phase and its dynamics would be boring, stationary. Now, that's what happens when I only have one particle interactions. When I have two particle interactions, there's something else that can happen. I can have, if I just look at e to the minus I ht E dagger tau prime psi 0. I can have my occupied electrons scatter from this additional electron. So one of the occupied electrons can scatter from the unoccupied to the occupied states. This occupied electron can scatter to another occupied state, such that I now have two occupied electrons extra and one hole. So in terms of diagrams, I have my electron in tau prime, which is occupied. It then scatters from an electron that sits below the Fermi energy, and I get a new electron, or an electron in a new orbital, and an electron in an orbital. So I start with one electron above the Fermi energy, and I end up with two electrons above the Fermi energy and one hole below the Fermi energy. So where in the case of just single particle interactions, you have to look at the propagation of a single electron. Once I have also two particle interactions, the propagation of one electron can change into the propagation of two electrons and one hole. And of course they can scatter even further, where you get propagation of 3 electrons and 2 holes, 4 electrons and 3 holes, etc., etc., etc. So in order to track the time evolution, where in the case of only one particle interactions, you just need to track the propagation of a single electron and all the other electrons stay where they are. In the case of Coulomb interaction, or two particle interactions, you have to look at the propagation of one electron, then the probability that it can scatter and become the propagation of 2 electrons and one hole, and then for each of them you again have to look at all the possible particle hole excitations that you can make. This is definitely possible, and we can look at these kind of expansions, and we will do that during this lecture and the next lectures, although in this lecture more at the level of just one particle physics, independent particle physics. But that's why having two particle interactions immediately makes everything more complex. The formalism and the things you can do and the techniques will be very similar, so it makes a lot of sense to first look at independent electrons. And once we have used a few examples of Green's functions there, we'll extend those to the case of interacting electron systems. So that said, how can we now get rid of our ground state wave function for the case of independent particles? And here I have to split, because what I say now is valid when you only have one particle interactions. When you have two particle interactions, you have to make a few more modifications. You can still define ways how to do that, but will deviate from what I define here. So we have one particle interaction only. We're going to define the vacuum Green's function. G plus of the vacuum, tau prime omega, is given by 0, and 0 is really the vacuum. We have no electrons in our system. We create a particle, we let it propagate, and we annihilate the particle. And we can also look at the advanced Green's function for the vacuum. But we'll immediately see you annihilate a particle out of the vacuum. Well, that's definitely going to be 0 because there are no particles. So we're left with basically only the retarded Green's function, G plus for the vacuum Green's function, and we don't have to look at G minus. So G plus of the vacuum, tau prime of omega, is what we will define to be the Green's function of our system, without a plus or a minus. And I can show you also why, because from this we can calculate both the retarded and the advanced Green's function. If we look for the case where our eigenenergy is larger than the Fermi energy, then we know that this is just a G plus, so the poles of our Green's function in K-space track the energies of the eigenstates. And the same is true for the case when omega is bigger than EF. So this has to be equal to G plus tau prime of omega. And we can do a similar argumentation for G minus, G plus vacuum for omega smaller than epsilon F. And this now tracks the poles of our Hamiltonian, but now for the energies smaller than the Fermi energy. So this is going to be equal to G minus. But of course, the only claim here is that the poles have the same energy. We still can have a sign change, and we can have a complex conjugated in there. And that's exactly what we have. So G plus of the vacuum is equal to G plus of your full system, where you take the creation and annihilations with respect to your wave function. G plus of the vacuum for omega smaller than the Fermi energy has the same poles as G minus, but we have a minus sign and a complex conjugated. So the imaginary part has the same sign, the real part has a different sign. And with that, the vacuum Green's function, or just our Green's function, is given as G plus tau prime of omega when omega is larger than the Fermi energy. This has a value. When it is smaller, this one is 0, minus G minus tau prime of omega complex conjugated. So we can write down our vacuum Green's function, where we no longer need to know the eigenstates or the ground state of your system, because you create particles and you annihilate particles you create particles into the vacuum. And from that we can derive both the retarded and the advanced Green's functions of our system that describes the propagation of extra electrons or the propagation of holes. Your eigenstates above the Fermi energy and your eigenstates below the Fermi energy. So from now on, most of the things that we'll do will be related to the full Green's function, and there we can then look how we can from this calculate properties of our system. Thank you very much for your attention. We see each other in the next lecture. Stay healthy.